we're going to start this discussion on the Navier Stokes equations. The Navier Stokes equations are some of the most important equations in fluid mechanics. It helps us balance forces on a fluid particle and come up with velocity distributions and things like that for simplified flows. To do that, we're going to start with the control volume version of the linear momentum equation. And here we have all our stresses, our shear stresses and our normal stresses on the surface of our differential cube. So we're going to assume that this control volume is very small, and that allows us to reduce the volume integral and surface integral to summations. The volume integral just becomes change in momentum over the volume, and then we have the summation over each face of the cube for our momentum in and momentum out. Then we define the body forces and surface forces. So we have the body force and the surface force in each direction, which are going to be basically the sum of gravity and the shear forces and normal forces on each face. So this is how we define these things, and it's based on that figure where we show all of the different surface stresses. So we have one of these in the x, y, and z direction. So for an incompressible Newtonian fluid, we can actually reduce the surface stresses because if the fluid is Newtonian, we can say that tau xy is equal to tau yx, and we can relate that to the viscosity and to the velocity gradient. We can also look at the normal stress, this sigma sub xx, which is a function of pressure, viscosity, and velocity, and then the velocity gradients. Here, P is the mechanical pressure, and this is the pressure we generally talk about and measure. The additional terms here represent the bulk viscosity and some compressibility effects. Now, we talked about incompressible flows during our discussion on the continuity equation, and in that case, del dot V is equal to 0, so this term right here is equal to 0. So if the flow is incompressible, this term is going to be 0 always. This term is the bulk viscosity, which is basically compressibility effects. It measures the transfer of energy from velocity to other modes like rotation and vibration. For an incompressible fluid, we usually neglect this bulk viscosity and we approximate our normal stress as the thermodynamic pressure. It may, however, not be totally negligible during rapid expansion or contraction, for instance with shock waves. However, most of the time, we just assume that the normal stress is equal to the pressure. So we can substitute this expression and this expression into these equations. And then we substitute these equations into the body forces and surface forces from our linear momentum equation. And when we do that, substituting all those terms and then dividing by the dx, dy, dz gives us these three equations. This equation tells us the x direction velocity u. This equation tells us the y direction velocity v, and this equation tells us the w direction velocity, in the velocity in the z direction. So the Navier Stokes equation, starting from the momentum equation, gives us three equations, one for each coordinate direction. And you can see here, here's our change in momentum with time, here's our acceleration terms, here's our body force, here's our pressure force, and this is the friction force, the shear stresses due to the viscosity or the friction within the fluid. Now, there is a more compact way to write the Navier Stokes equations using gradients and vectors. Again, it's important to note here that there are three different equations in this single expression because this is a vector. It has an x, y, and z direction. This is an x, y, and z direction. This is a gradient with an x, y, and z direction, and so on. This is important because we can use the definition of the gradient operator for cylindrical or spherical coordinates to simplify some of these types of problems. So we can use this basic equation and just look up the gradient operator in different coordinate systems to come up with final versions of these three equations in new types of coordinates. It's important here to note turbulence. If you consider flow through a pipe, if we measure the velocity as a function of time, for small Reynolds numbers, or very slowly moving fluids, we basically see that the velocity maintains its value as the average almost all the time. It doesn't change very much. However, as we go to higher Reynolds numbers, to faster moving fluids, we start to see that the velocity changes. It oscillates around some average value. So here, laminar flow, Reynolds numbers smaller than 2,300 for flow in pipes, are very smooth. They don't have a lot of fluctuations. Turbulent flow is very complex. The fluctuations are chaotic. They're not random. They're actually governed by chaos theory. But the problem is that they're so chaotic that they're very difficult to analyze. So most of the time, we look at turbulent flows empirically rather than analytically. And so the question becomes, how do we address these turbulent effects in our differential equation for fluid motion? So in engineering approximations, usually what we do is we define the variable by defining an average and a fluctuating value. So what we do is we take the actual signal, the actual density, the actual velocity, and then we average it, and that gives us rho bar and u bar. And then we take the actual minus the average to give us the fluctuation. So here we can convert the actual signal into the average and some fluctuating value that fluctuates around 0. Now there are various rules regarding this average process that we have to follow, but the end result is that we have an averaged continuity equation. Here there's no additional terms or anything, there's no real surprises, but we also end up with the Reynolds averaged Navier Stokes equations. The Reynolds averaged Navier Stokes equations are called Reynolds averaged because we have these additional terms that account for what we call covariances between the velocity fluctuations, where we have to average the product of the two. This is used in many commercial CFD codes, and then these new terms are called Reynolds stresses. They're not actual stresses, like shear stresses, but they behave like stresses. They're actually what we call additional momentum fluxes. They're actually additional terms for momentum into the control volume and momentum out of the control volume by flow due to turbulent mixing. The problem is that if we're going to use these equations, we need to develop models for these Reynolds stresses, and that's a pretty complex topic. In fact, there are entire graduate level courses on this topic. So we're going to leave it for later and just acknowledge that if we're going to use the Navier Stokes equations to predict turbulent flows, we need to have some model in place for the effects of turbulence through the Reynolds stresses.